Hello, a great welcome to Idea Statica tutorial. Myself Jarajan P. This is tutorial number 21. Here I will demonstrate the stiffness analysis of a base plate connection provided under a rolled steel column section. Joint stiffness classification is done as per the Eurocode EN 1993-18. So the geometry of the base plate used for the stiffness analysis is shown here. In this tutorial, we shall evaluate the moment of resistance of the base plate connection shown here, the initial rotation stiffness as well as the secant stiffness, the rotation capacity of the connection as well as the joint stiffness classification. Now the first question every engineer will ask is why the stiffness analysis of the base plate connection is very important. So as we are aware, in the analysis and design of steel structures, the column bases, popularly known as the supports, are assumed to be either rigid or pinned. The distribution of internal forces stored in displacements within the structure are highly dependent on column base stiffness. In many situations, it is observed that the column base connection is neither rigid nor pinned as assumed during the analysis, but actually semi-rigid during the analysis, and making these analysis results unreliable. Estimation of the column base stiffness ensures the validity of assumptions made during the analysis. The estimation of column base stiffness is in particular very important in cases where the structure is subjected to lateral loads such as wind or earthquake. So referring the sketch for the structure shown here, the question is, during the analysis, shall we assume or support as pinned, rigid or semi-rigid so that the analysis results are acceptable? Now the European Code EC3 employs the component-based verification for the evaluation of rotational stiffness of connection, and it uses basically the stiffness coefficients of the components constituting the entire connection, that is designated by Ki, and the rotation stiffness Sj is calculated as Ez squared divided by mu into summation of 1 by Ki. A typical moment rotation curve as presented in the European Code EC3 is shown here. As you can see that in the initial parts, the M5 curve is a straight line providing us a measure of the initial stiffness Sj, I and I, and the M5 curve will be nonlinear afterwards. The EC3 assumes that a nonlinear relationship could be assumed for M5 relation up to a value of 2/3 of mgrd, where mgrd indicates the moment of resistance of the connection. So let us start Idea Statica tutorial number 21. Please note that the link for the playlist for all the earlier tutorials are provided in the video description. So please subscribe to the channel so that you are notified as and when new tutorials are uploaded in the future. So the model for the tutorial is shown here. So in this tutorial, basically we perform three types of analysis. In the first analysis, that is known as the EPS analysis, that's a plastic strain analysis, we will check a base plate of a given geometry and with a given set of angle rods for a given set of loads. And in the second stage, what we do is that we perform an analysis in order to calculate the joint design resistance, that is a DR analysis that will enable us to evaluate what will be the design resistance of the given base plate. That means how much maximum moment a given base plate connection can take. And finally, we will carry out an ST, that is a stiffness analysis, in order to classify the designed base plate connection, whether it is a rigid one, whether it is a pinned one, or it is otherwise a semi-rigid connection. So that is the first focus on the plastic strain analysis, wherein we will check this assumed base plate connection for a given set of loads. So before proceeding for the EPS analysis, let me quickly introduce you to the various components and the manufacturing operation used here. So here I am not going to tell you in detail the various manufacturing operations because these things are already being dealt in detail in the various earlier tutorials. So here you can see that the column used is an HE360A. It is a vertical one, so we have set the pitch angle as 90 degrees, and we have used an NVM model. Now we go for the base plate manufacturing operations in order to model the base plate as well as the hangers. And this manufacturing operation I can show you here. So this is my base plate manufacturing operation. So wherein I will set all the various parameters required to define the material grades, the location, as well as the dimensions of the base plate. So as you can see that, so this base plate, it is made of S275 grade material and so having a thickness of 25 mm, and the various offsets are defined to uh, perfectly define the edges of this base plate with respect to the rolled steel column section. And the anchors, as you can see, that it is an M24 grade 4.6 bolts with an anchor length of 600 mm, and it is for the given tutorial kept as a straight. And the rows of the bolts, as you can see, there are two bolt rows, one each corresponding to the bottom flanges as well as the top flange. So they are kept at 75 mm from the rolled steel section profile, and the distance between these bolts are being kept at 125 mm. Now coming to the welds, here what is done is that no connection is envisaged to the flanges, and what we do is that we use straight away a 6 mm both-sided fillet weld for connecting the web of the column to the base plate. Now coming to the foundation block is of grade C2530, and the edges of the foundation is kept at an offset of 500 mm from the base plate with an associated depth of say 1000 mm, and the shear force is assumed to be transferred through the friction mechanism, and the standoff is considered as the direct. Now we shall go straight away for the manufacturing operation stiffening plate, and this manufacturing operation will be used for modeling and specifying the shape of the stiffening plate that is shown here. So here, as you can see, that the stiffening plate operation, let me just show you. So this is your stiffening plate manufacturing operation used to define the stiffening plate. So you can say that it is defined to be a 275 grade with a thickness of 10 mm, and the shape of the stiffening plate is specified through the B1, B2, H1 and H2 parameters, and the various notches are generated through the editor capability available here, and by specifying the various the chamfer parameters, okay, as shown here. And then the rotation of this plate is stiffening plate is kept as 90 degrees, and its location is kept at 175 mm so that it matches so that is the surface will match with the flanges of the column. So the similar is the set of command or the parameters used for the description of the other stiffening plate as shown here. So you can just rotate the model. So this is a stiffening plate that is being generated with the SP2, and you can find that the parameters are exactly the similar. Now what we do is that we go for the plate cut command, and this plate cut command is used for providing the various welds. For example, here pcut1, what does it do is that it connects SP1. SP1 is nothing but it is our stiffening plate, that is this plate SP1, and the BP1. So here what is done is that this is stiffening plate, it is a butt welded, okay, it is a butt welded to the column base plate. So we will use pcut1 to specify this connection. So you can see that SP1 is the modified item, it is cut by BP1, and the connection is done through a butt weld. Similar is the pcut2, which is used to ensure the butt welded connection between the stiffening plate SP2 as well as the base plate. Now you will find that there are a set of commands: weld 1, weld 2, weld 3, up to say weld 6. So let us just see regarding the weld commands that we have used for the first the stiffening plate SP1. So as weld 1, you can see that this is also a manufacturing operation. So is this one, you can see the welder contact. Okay, so how easily you can handle the various manufacturing operations, that tells you how fast you can generate a model in Idea Statica. So in weld 1 you will find that the SP1, okay, that is, this is my SP1. Let me just zoom the model a little bit. Yes, this is my SP1. Okay, it is connected to the column bottom flange, that is this one, and the SP1, the edge index, the edge that is welded, it is a 6. Okay, so that means this weld 1, it develops or it creates the welded connection between the top of the stiffening plate and the column flange. Now go to the weld 2. It's a similar connection wherein the column edge 2, that is the column edge 2, it is welded to SB1. That means we are talking about this particular connection. Okay, so the similar is the case weld 3, wherein we have developed a similar kind of a welded connection between the stiffening plate as well as the column flange, so that can be easily seen through. So we are talking about this weld. Okay, this weld that is connected between connection between the stiffening plate as well as the column flange. And please note that here that the respective edge, okay, to be welded, it is identified through the edge index. Here for example, edge index is 4. So the similar kind of a 3 welding operation is also required for my other stiffening plate SP2, and that is being done through the weld 4, weld 5 and weld 6. So it's a very simple base plate connection used. Now having done that, let us straight away go for the specification of the loads. So you can see that this column will be checked. The base plate connection will be checked for an axial load of 200 kilonewton. That's in compression, shear load of 30, and there is a major axis moment of 125. So let us straight away proceed for the EPS, that is a plastic strain analysis, so that we will know whether this given base plate arrangement is good enough to withstand the specified set of loads. So just press calculate button. Okay, so we find that it's a very simple model, so the calculations are done very fast. So here we find that almost all the components like the anchors, plates, and the welds are efficiently being utilized, and we don't have any kind of a problem with a concrete block. That means this assumed base plate connection is good enough to withstand a load of 200 kilonewton axial and a MY of 125. Now, having said that, we would also like to know what exactly could be the maximum moment which this connection can resist. So for the set purpose, what we do is that we copy the same model and we make another model. Here I have made it as say base plate 1. So just press it. So here, so it is not base plate 1 because it should be base plate 2. Okay, you can just copy and you can use the same model. Yes, so we have seen that this base plate connection is good enough for resisting the given set of loads. Now we'll see what could be the maximum moment of resistance of the section. That is, what could be the maximum moment which this base plate connection can withstand, for which we'll perform an analysis type known as the joint design resistance. Okay, so please remember one very important thing, how the way in which the software Idea Statica proceeds is, it will because the moment of resistance is a function of the axial loads, so it will keep this working load at minus 200 and then go on incrementing this moment my till the components are being fully utilized or it meets the target strain level criteria. Okay, so let us quickly do the calculation. Okay, fine. So we find that the DR calculation, that's the joint design resistance calculation, is complete, and here we have the results. And we find here is that the load factor, that is, the joint can take an additional 37.2 percentage. That means the factor reported here is 137.2. So please note that in the present case, this base plate was designed for a moment of 125 kilonewton meter. It does mean that you can take the base plate up to a maximum moment of resistance of 125 into 137.2, which approximately will work out to be 171.2 kilonewton meter. So remember, the design moment of resistance that we calculated by this analysis is around 170 kilonewton meter. And here just below you will find that a small plot, and this small plot will provide you on the y-axis. It is not the moment, it is the maximum additional percentage of the load which the base plate can take, and along the x-axis you will find that the strain levels are being marked. So here you will find that the maximum percentage is around 140, that is clearly written here as 137.2. So that concludes our the DR, that's a joint design resistance analysis. Now with this information in our hand, what we can do is that we can straight away go for the stiffness analysis. So what I will do is that I will just use my base plate 1, and here please note that for base plate 1 I have kept the analysis type as ST, that's a stiffness analysis. And here I would like to tell you that one more parameter is required. So that means for allowing the Idea Statica to perform the stiffness analysis, here you will find that in the under column 2 additional parameters required. It is specifically written for the stiffness analysis, that is the theoretical length. What should be the theoretical length for My and Mz? Here I have used it as 5 meters each, and this will be used by the Idea Statica for calculating the limits specified by the Code 3 for the various stiffness parameters. So having said that, let us other parameters will be the same. So let us straight away go for the computation of the joint stiffness. So press the calculate button. Yes, our stiffness analysis is now complete. So let us go for check button so that we will see the rotation stiffness parameters. Press the rotation stiffness. Here you will find that the various parameters are mentioned over here, and the M5 curve is provided just below this. And in order to get a clear understanding of the various terms involved in the M5 curve, so let me take you to the report section so that we'll be able to see each and every symbol properly and clearly examine the various quantities provided in the Idea Statica stiffness analysis results. Look here. So this is a very beautiful curve. So here remember that the stiffness analysis will basically provide you an F5 curve with the moment being plotted on the y-axis and the corresponding rotations of this joint being plotted on the x-axis. Remember that the rotations are in radians. Now this is my M5 curve. So as you can see that up to some particular point it is linear, and thereafter it turns out to be non-linear. Here you will find that Idea Statica has provided some values here. For example, MRD, that is the maximum moment which the joint can resist. We have already performed a DR analysis, that's the joint design resistance, and we already found out that the joint design capacity is of the order of say 170. The same thing, it is 171.3 kilonewton meter. So this is my MJRD, that is the joint design resistance. Now, as per the Eurocode, what we need to do is we need to we need to draw a line at a 2/3 of MJRD, that is 114.2. So this is the line that is being drawn at 114.2. Okay, and then what we need to do is that we need to draw a tangent at this point so that we get an approximate equivalent linear relationship. Okay, now here let us examine the various parameters that is being provided by the Idea Statica. So that is given in, I think, the next table. So is this one? Yes. So let us investigate. Here it's a rotation stiffness parameters, and MJRD. This is nothing but it's a joint design resistance of 171.3, which we have already performed under the DR analysis, that is marked here. So this is 171.3. So now what will be the maximum rotation of this cross section under this MJRD value of 171.3? So what we need to do is that under this moment draw a line where it meets the M5 curve. This value somewhere around say 11.5. So this is what here it is written. Yes, 5C, that's 11.3. So now let me explain you, because the symbols are strictly as per the code requirements, so you must be very comfortable with the symbols. So 5C, yes, the rotation capacity, that means the section will undergo a rotation of 11.3 milliradians under a maximum capacity of 171.3 kilonewton meter. Now you will find that the main parameters, the very important parameter that is used for the stiffness classification, that's the initial stiffness, SJINI. Here again, if you have a doubt, go down and check it. SJINI is the initial rotation stiffness. Now what is done here is that, so under an applied moment of 125, it has obviously calculated, okay, what would be the corresponding initial rotation stiffness. That works out to be 28.8. So 28.8 mega Newton meter per radians. will be my initial stiffness. Now what you need to do is that this initial stiffness value, which is already straight away marked over here, this is a SJINI. Okay, SJINI. This is the initial stiffness. Okay, that's a 28.8 meganewton meter per radians that you need to compare with the limits given by the Eurocode. There are two values, that's SJR and SJP. What are this SJR and SJP? So SJR, as you can say that is nothing but, so look here, this is my SJR, that's a limit value for a rigid joint, and SJP is the corresponding value for a nominally built joint. So in this new case, you will find that the calculated value of the initial stiffness of 28.8 lies between these two extremes, one for a pinned connection 4.8 value and the other for a rigid connection 241.5. It does mean that the given connection can be classified under a semi-rigid connection. So you will find that in our calculations in the normal analysis procedure, we straight away blindly assume it as a rigid connection. So in many of the cases, you will find that the connections really comes under the semi-rigid type, thereby influencing the distribution of the story displacements as well as the moment distribution between the various components. And here you will find one more term that is known as a secant stiffness, SJS. What is the secant stiffness? Secant stiffness is nothing but it's a moment rotation slope, okay, that is specifically calculated at the applied moment. So what we need to do is that we know that the applied load is 125. So at 125, okay, so you'll find that here this is a 125 kilonewton meter. At this point, you draw a line. So this will be the point, and corresponding to this point, what we do is that at this point we directly join with the origin. So we'll be getting the secant stiffness. So secant stiffness means it's a stiffness corresponding to the applied moment. Okay, and we'll find that the associated rotation is equal to 5.4 milliradians. So this is all about the stiffness analysis. If you have any queries, please reply through the YouTube channel. So that's all. Thanks a lot for patient hearing. Have a nice day.